Welcome to lecture 44, which is on digital image enhancement methods. So once we have learned the georeferencing and resampling technique, in this lecture now we are learning that if the quality of the image is poor, how to improve the quality of the image so that now we can identify different objects or at least the training sets which are required for classification of the image. So prior to classification, enhancement methods are required, and this is what we are learning, that what is the utility of this enhancement methods in this lecture. So we begin the lecture. When we are doing the image pre-processing, so when the image is procured from the agency, then you have to apply, for example, you have learned how to apply radiometric corrections, how to apply geometric corrections, and now you are learning that how to improve the contrast. If the contrast is not good, if I am not able to identify or recognize the objects, then probably I cannot create a vector map, I cannot prepare a thematic map, uh, also I cannot properly select the training sets which are required for classification purpose. If there is a noise present, we have to remove the noise also in the data. Then a transformation of the images we are going to learn in the next lecture. So let us see the image enhancement, how we can enhance the image, improve the contrast of the image. So we are doing actually three ways. One is the contrast manipulation. So we are changing the contrast of the image, we are stretching the DN values, we are thresholding the DN values or doing the density slicing of the DN values. The second is the filter process, filtering. We are applying the filters. So that is what we call the spatial feature manipulation, and through that we are enhancing the edges of the different objects and the features which are present. And the next is the multi-image manipulation, where we are doing the data merging and data fusion techniques. So we will discuss the first one here in this lecture, that how to carry out the stretching of the DN values and carry out the thresholding and density slicing to improve the quality. Now when we are doing the image enhancement, as I told you, we are doing contrast manipulation, contrast interpolation. What is contrast? Contrast is, if I know what is the minimum value in my data set, what is the maximum value of my data set, and if I take the ratio of that, then I know the contrast ratio. What is the contrast ratio? So I have to improve this contrast ratio, or the minimum contrast, the maximum contrast, so that my image occupies the whole range of the DN values. As we know, in the 8-bit data sets, there are 256 gray levels, 0 to 255. So all the gray shades, if they are present in the image, my image is considered to be the best as far as its visual quality is concerned. So for visual interpretability of the image, we are changing or manipulating the contrast or stretching the contrast of the image. So technique of enhancing the image so that it is now much more suitable to me for a particular applications or for identifying the object, that is called the enhancement of the image. We can see that on the left side there is an original image, it is quite dark image, hardly features are visible to me. So if it comes to the vectorization of this image, or it comes to the identification of the certain features, control points, identification of the training data sets, then cannot be done. The right side shows the enhanced image. So once the contrast is stretched, the image becomes enhanced, and one can identify many features and can see the varying gray shades in the area. Now as I told you earlier also, that the image can be represented in the form of histogram. Graphically you can represent the image. So this is the graphical representation of the image in the form of the histogram, where digital numbers are plotted on x-axis, the occurrence frequency is on the y-axis. So, if I am doing this and I am getting a normal kind of a distribution, so if I draw a curve, this is a normal kind of a distribution where I am getting the peak at the center in the middle, but I am getting another peak also. Although this peak is smaller, but there is another peak afterwards, and these two peaks are indicating me that there is a uh, very peculiar object, there is a very peculiar tone here present, and because of that peculiar tone, I can try to identify that particular object. So, the histogram, the uh, the range which is occupying, the histogram, the range occupying, it actually tells me the quality of the image. If the histogram is not occupying the full range of the DN values, then probably the image requires some kind of enhancement. So, histogram is one graphical representation of the image which actually determines the quality. Histogram is a graphical representation of the DN values, and in this slide you will see that there are different shapes of the histogram, and sometimes looking at the shape of the histogram we can make an assessment about the image, whether that requires enhancement or not, or what kind of features could be present in the data set. So, if we see the first histogram, which is a Gaussian distribution, a normal distribution, here the data is well distributed throughout. So, we can see higher values are in the middle, and then there are lower values in the low frequency, and the very high values are also in the low frequency. But this is very difficult to obtain. Most of the images will have a different kind of a shape, sometimes the skewed shape and sometimes the bimodal shape. So, if we have the skewed shape, there are two categories of this. One is where the high peak is towards the higher values, as you can see in the first slide, and this is what we call as the negatively skewed distribution. Another category is where the peak is towards the lower side of the DN values, and this is called positively skewed distribution. So, most of the time we will find that the histogram is not normally distributed, but it has slightly skewed shape. So, in a negatively skewed distribution, we have very high values towards the higher side. So, that means the objects are much brighter which are present here. So, the examples could be the snow, the bare soil, etc. But on the other hand, the positively skewed distribution, where we will have the peak towards the lower side, that means the most of the DN values are low and there is absorption by those features. So, we have examples like water, example like forest area and the wet soil. So, they will give me very dark values. We may have a distribution like a bimodal distribution. In bimodal distribution, there are two very clear cut distinct peaks are there, and these bimodal distribution is giving me some indication like there are two distinct objects, two broad categories of the objects which is present in my data sets. So, looking at the histogram itself, one can actually identify what kind of a image is this and what kind of enhancement is required in this image, so that we can identify the objects very clearly. Now, if you look at the other histograms, here also we have peaks, but we do not have the peaks at the center. Either we peak at the higher or peak is towards the lower values of the histogram. So, that means these kind of images where the distribution is not normal, these kind of images would require enhancement. So, it is obvious from the histogram itself that we have to proceed for image enhancement process. Now, if you look at the histogram, as I told you, that it is conveying you the quality. Why? Because it is not occupying the lower range as well as it is not occupying the higher range of the DN values. So, values are missing, the values are confined in the center only, and then also there are two peaks, one peak is here, another peak is there. So, one can see from the image also it is a poor contrast image, and the one peak is coming from the image of the boy and another peak is coming from the background which is slightly darker. So, here, but overall if you see the quality of the quality of the image is poor, you have the image toward the darker side, and the reason is that the values are the DN values are not well distributed over the entire. So, that means even if I do not look at the image, I look at the histogram, probably my conclusion is that this kind of image requires enhancement before we start step for the classification. Now, in the image histogram, there is one more interesting thing. Interesting thing is there is an image here on the left side and all the pixels have the DN values. If I plot a histogram of the image which is on the left side, and now what I do is I jumble up, reshuffle the pixels. When I reshuffle the pixels, I am not changing the DN values of the pixel, I am changing their geographical locations, the coordinates. So, pixel number 1 has probably become pixel number 10 here, pixel number 2 has become pixel number 100, so like that. So, if you jumble it up now and see the image, now it is very difficult actually to identify what kind of an object it was, whereas you can see the object in the left image, the same object is not visible in the right image, although you have not changed the DN value, you have only reshuffled their locations. But if I look at the histogram, histogram will remain same because histogram is the DN values versus the frequency of the occurrence. It does not tell you the geographical location of that particular pixel, xy coordinate of that pixel. So, this histogram will not change, but the that means the information content remains same, but we are not able to see the even after jumbling up, we are not able to see the object from this. Now, there are different uses of the histogram. When we look graphically the image in the form of the histogram, there are different uses, like if we can use for image enhancement process, we can use for compression of the image. This is another area where big data set is compressed together, so that the sharing of the data, transforming the data is much easier. So, compressing the data and yet maintaining the quality of the image. Then image segmentation. So, if we have the images with several features and we are interested in one or two particular feature, then we can do the segmentation. Looking at the histogram, we can take some DN values and categorize them into one category and other remaining DN values into the other category. Object recognition based on the statistical features. So, these are some of the uses of the histogram. Now, we have to modify this histogram. So, why we have to modify? Because our histogram is either positively skewed or negatively skewed, or we have we do not have the peak is missing. So, the histogram modification is very important when we find that the distribution is not a Gaussian distribution, it is not a uniform distribution. So, in the enhancement process, when we are doing the enhancement of the data set, in an enhancement process we are doing histogram stretching and histogram equalization. So, here we are dealing with the DN value, gray level values. So, two processes we will explain here, and then there are spatial domain and the frequency domain, which we will not deal in this lecture, we will deal in another lecture. So, histogram stretching and histogram equalization. Name itself is suggesting that you are stretching the values of the histogram. In another case, you are equalizing the frequency, almost equalizing the frequency. in the histogram. So let us learn what these two different techniques are there where we are dealing with the gray level values and the DN values. Now it's very simple. When you are doing the transformations of the images, there is one image which is to be transformed and we should get the enhanced image as the output image. So here there is a mathematical representation where gxy is my output image, enhanced image, and then there is a function which we are applying to my input image data. So we can have a point transformation, we can have a domain transformation. In the domain transformation, basically I am taking a group of pixels. I am not working here pixel by pixel. A group of pixels are taken in this transformation, but in point transformation you can see that one pixel at a time will be taken, some transformation is done for that pixel, and then we can get the new values which are the enhanced value at that particular location. So this is the result of the image enhancement here. My original image, where you can see there are certain vehicles which are visible but not that clear. If I look at the histogram also of this data, you can get a very high peak all of a sudden. This is not a gradual rise and peak at the center, and there are certain values which are missing. But when I stretch the values, do the enhancement, so after stretching the histogram becomes like this, which is shown at the bottom. So values are spread now all along the region, and as far as the quality of the image is concerned, so if I display the image with this new enhanced values, I can now get the better visibility in the image. I can identify not only the vehicles but the surrounding features also. So my mapping work or my measurement work become much better on this image. So this is the image on the left, which is quite hazy kind of image or underexposed image. You do not see a better contrast here, but after enhancement one can see a better contrast. One can see uh, the uh, the runway and the urban areas all very clearly seen on these images. So this is the advantage of enhancing the image. If the image quality is not that good, where features cannot be identified, we can do that. Now we cannot, our eye cannot differentiate between various gray shades because of the limitations of the eye, but digitally we can do that. So this is what we are doing actually. So this example shows the left side histogram of the original image, where some values in the lower range and some values in the higher range they are missing. But when you are stretching this histogram, when you are like to improve the contrast of the image, and the values are actually now occupying the whole range of the histogram, and this is called the contrast enhancement, because we should get the better contrast image. Please remember here, you are not actually adding any extra information to the original data. You are simply redistributing the values. So values which are confined into one region, now they are confined to the whole range of the data. So we are not adding any additional information to the data in order to improve its visual quality. So this is what is image enhancement technique is doing. So in the contrast enhancement, when we are doing the enhancement of the contrast, so it will just expand the narrow range into the full range. Like 8-bit image, my full range in 8-bit image is 0 to 255, but my original image is occupying between 10 to 60 only. So 0 to 9 is missing and 61 to 255 values are missing. So after the contrast enhancement, the stretching, the image will occupy the almost the entire range from 0 to 255 and redistributing the pixels. So this is what it is done in the contrast enhancement. And when we are talking of the linear contrast enhancement, we are using a very simple kind of a mathematical equation where we should know in our original image what is the minimum value which is present. As I gave you the example, if 10 is my minimum value, so min is replaced by 10, and if 60 is my maximum value, then in place of max here the 60 is replaced. So if I know what is my minimum value and what is my maximum value present in the data set, which is very easy to determine, and now I use this linear stretch relationship, linear contrast enhancement relationship, and in this relationship if I take pixel by pixel transformation. So if I take first pixel and replace here the dn value of the first pixel and apply this simple relationship, it is multiplied by 255 in case of the 8-bit data, so that the range becomes between 0 to 255. It does not fall within the small range. So this is a constant which has been multiplied to all the data. So we are doing that the point by point enhancement to the entire image and getting the new values for each pixel and replacing that value at that particular pixel location. So this is how we are getting the new sets of dn values when we are doing the contrast enhancement, but the pixel location remains same, it does not change. Disadvantage of this method is that many display levels to rarely occurring image values, as it does not it does to the frequency occurring values. So when we are using this kind of a linear stretch, you can develop some kind of a algorithm also here which will take care of, so that your output is not more than the 255 in case of the 8-bit image. Okay, so this is the way one can develop the algorithm just to cross check the range, so that the output range is always between the desired range. Now if you remember that figure which I have shown you earlier, this is the boy and this is the histogram of that picture image which is to be enhanced. After enhancement, after the stretching of the values using linear contrast enhancement techniques, we are getting very good, very sharp image now. In the sharp image we can see not only the object very clearly, but also the background details are also very sharp. So these are the images which are preferred when we are talking of the visual interpretation and we are identifying certain details, or we are carrying out the measurements from the data. So this is another example of the linear enhancement here, that different linear enhancement are done with the original image. This is the original image and this is after the enhancement. One can get very sharp detail and carry out the interpretation from the sharp details. So interpretation can be carried out from this image much better way, because this image is not giving me enough information visually. So I have improved the visual quality of the image by using the linear contrast enhancement technique. So on the left side is the satellite image where there are a lot of agricultural fields are there, but not very clear. The image is so dark here. After the linear stretch enhancement, the image has become very sharp. One can identify road very clearly, the urban area, the agricultural land, so that all can be clearly seen. But as I told you, the color image is much better to the human eye in order to identify more and more number of objects. So this is the color enhancement. So on the left side is again the original image in 3 colors, RGB, and then here we are using actually the same image after the applying the linear contrast enhancement to all the 3 bands, and we are getting very sharp image here. So the information content has improved a lot by doing so. The second method here, it is called the piecewise linear contrast enhancement method, and the piecewise linear contrast enhancement method, uh, we are doing the enhancement into the pieces. So instead of applying the algorithm to the entire uh, image in one go, we are actually doing that treatment to a certain range. So applying, for example, enhancement, linear enhancement in this range in a slightly different way as compared to the middle range and as compared to the higher range. So you can see that the whole of the grayscale range has been divided into several pieces together. So there is a breakpoint here and there is a breakpoint here. So we have now three pieces in this example, and one piece and the second piece and third piece, we are not applying the same linear method, but we are enhancing the one part according to the desired object which we want to identify. So we can, in the piecewise linear contrast enhancement, the advantage is that instead of applying the algorithm to the whole image, we can apply to a certain piece. Suppose in one area I have the urban setup. So I want to enhance the urban setup, I can only enhance that particular part of the region. So this is the result of the piecewise linear enhancement original image, which is again not very good as far as the details are concerned, but we can see much more detailed information from the images which have been now enhanced using piecewise linear enhancement techniques. The other techniques which are logarithmic enhancement technique, where the simple equation like y is equal to a log e to the power bx is used, where a and b are again constant, x is the digital value of the pixel which is to be enhanced, and y is the output. So this is the curve of the logarithmic enhancement. You will see that there is a very sharp rise, and then the curve becomes almost kind of a stable. So this logarithmic enhancement is lower amplitude of input value, it will expand, and this enhancement is suitable when when you have actually a slightly darker kind of a shade kind of a image. So I can show you the results here, that this is my original image, and after the logarithmic transformations, this becomes the transformed image. So the image which was actually quite dark, now the pixels which were dark has become much lighter. So that is the effect of this logarithmic enhancement. So if you have a image with a lot of dark pixels, one can apply it and get the enhancement in this area. The second is the exponential function. Exponential is the reverse process of the logarithmic. So here equation is y is equal to a e to the power bx, where x is again the input digital number, y is the output, a and b are the constant quantity. So in the logarithmic curve, it was rising, and then there was a kind of a stability horizontal. It goes opposite to that. So it actually slowly rises, and then there is a sudden steep growth. So the nature is just opposite. So in other words, I would say that wherever the area is much lighter in reflectance, this particular exponential enhancement is going to enhance those areas very well. So features could be like highly reflecting features would be brighter areas in the image. So one can see that example here again, that this was the brighter image, a lot of reflectance coming from the area, and this is the enhancement doing the exponential transformation. The next one is the histogram equalization, very popular technique, and a lot of people have used that histogram equalization. So sometimes on some of the images, linear enhancement technique or logarithmic or exponential doesn't work very fruitfully, where histogram equalization is giving me very good results. So the whole idea of this histogram equalization is that stretch the values in such a way and redistribute, so that the frequency becomes almost equal. So it does not make exactly equal, but almost equal. As you can see from the original histogram, there were some values which were actually giving higher frequency, lower values were giving higher frequency, and there were higher values which were giving slightly higher frequency, and in between the frequency was not that high. Now after histogram equalization, the frequency become almost equal, and this kind of a redistribution enhances the features very well. As you can see in this diagram also, this is the image of a skull. In medical science also people have used histogram equalization, and this is my original data, and this is after the enhancement of the skull. So lot of diagnosis, when you have the enhanced images in the medical science, lot of diagnosis have been actually corrected. The histogram equalized image at the bottom and the original image is shown in the top. So one can identify, once the image is sharp, once the image is bright, one can identify the objects much more clearly. So results of the histogram equalization on the right and the original image is in the left side. Next is the gray level thresholding, and in the gray level thresholding, what we are doing is here in the gray level thresholding that we are identifying a certain range of the desired object. Suppose the desired object is the water feature. So I must identify what is the DN value range of the water feature in the satellite image, and then try to give them value as 1 and others value as 0. So I will make a bit image from that, 1 and 0. So 1 is the object which is of interest, and 0 means the other objects which are present. I want to suppress them. So 0 means that area would appear as a black, and 1 means that area would appear as a brighter to me. So brighter area is the area which is of my interest, object is my interest, and the other areas I have suppressed by creating the binary object. So these kind of images have also been found very useful when we have to identify the object, when we have to see the shape of the object very prominently and suppress the surrounding features. So one can see the effect of the thresholding, and this is the original image of a person, and this is the after thresholding using some kind of a threshold values. So Landsat image, one can see the different threshold values have been used in the Landsat image. Threshold value 6, threshold value 10 in the next image, then 16 and like that. So if you are using the different threshold values, then you are able to see the different features which are very sharp and very prominent from the images. So as far as the shape is concerned, one can identify the shape, one can locate the objects using the threshold. Now this threshold has been used in medical science also. The entire image enhancement process is very useful when we have CT scan, we have X-ray images, we have MRI scan. So this is again the scanning of the skull portion, and then some kind of a thresholding has been done of the gray level values, and when you are doing the thresholding, now you can see that the different parts here are showing their edges, and by looking at the size, by looking at the shape, one can properly diagnose, can also identify that if some thing is going wrong here, some part is malfunctioning, then also that can be identified by using the different threshold value. People have used this image enhancement technique for law enforcement as well. For example, identifying the registration plate from the images, video images of course, and then in fact enhancing the documents, court documents, or there are relevant documents where we are putting up the thumb. So sometimes if the ink is smudgy, or the thumb impression is not so clear, then we can do this image enhancement and probably improve the quality of the image. So apart from the mapping science, using in the satellite image, it has a lot more applications in the other way. So whether it is the law enforcement, where we have the original fingerprint and this is after the histogram equalization, one can see the fingerprints much more clearly, or in the medical science, this is the brain scan image and this is after histogram equalization. So there are different areas, there are different fields where people are using these image enhancement technique. So again, one more example where you can see the entire skeleton of the body image. So left image is not very sharp, not very clear, but after applying the enhancement process, now one can see that the entire body skeleton has become very clear, and now one can carry out the desired study from these enhanced images. So these images have a lot of applications. Thank you very much. This is all about the enhancement lecture.